Good morning, everyone. My name is Tracy Ruddig, and welcome to the American Iron and Steel Institute's Efficient Steel Bumper Beam Design webinar. At this time, I'd like to introduce John Catterall, Vice President of the Automotive Program for AISI. John?
Thank you, Tracy, and good morning and welcome to everybody. Thank you for joining us this morning. AISI is pleased to release the 7th version of its Steel Bumper System Design Manual today, which you can download from our website. Now I'd like to introduce our guest presenter today, Stu Brown, formerly System Architect for Bumper Systems at General Motors. Stu will be walking us through why increased high-speed crash requirements have created a need for higher strength bumper beams and how higher mass vehicles such as battery electric vehicles will create additional performance requirements for bumper systems in high-speed crash, due mostly because of the increased mass of the vehicle. Stu retired from General Motors after working on bumper systems for 31 years. And his last 13 years were as the system architect. And actually, I worked with Stu at General Motors. He was responsible for understanding global crash requirements and the engineering know-how to set up, package, and meet requirements for bumper systems in each global region. So he has global knowledge for all the requirements around front and rear bumper systems. And now we will hear from Stu and the launch of AISI's Efficient Steel Bumper Design. So welcome, Stu.
Welcome. Thank you, John. Just like to welcome everybody to this webinar. Good morning, good afternoon, good evening, depending on what region you might be from. This presentation really is a culmination of what the bumper team at the American Iron and Steel Institute has been working on for probably about the last year and a half. And we originally targeted this presentation for the Great Designs in Steel conference that didn't happen last month, and so we thought there was enough information though here we wanted to get it to you in the form of a webinar. So it'll be about 30 minutes, and how we've kind of pulled this together into some information for you. We'll look at the agenda, kind of what the structure we're going to look at here is, just to kind of level everybody. We'll look at kind of the general status of what bumper systems are right now. Look at the bumper system performance trends for both low speed and high speed. Also looking at new requirements that are affecting the bumper beam materials that we're choosing. A benchmarking study we did on beam material. Then look at a case study that we put together for front mid-size car bumper beam. And that will then draw some conclusions, and we'll introduce the version 7 of the new Steel Bumper Systems Manual. So let's begin. So just to give you a general status of where we are with bumper systems, bumpers have become very integral to vehicle styling. In some cases, it's difficult to know exactly where the bumper starts and where it stops. I mean, this is in contrast to maybe when the bumpers first came into the market, where you had a vehicle styled and the bumpers looked very add-on to the vehicle styling. We're not seeing that now. Bumper systems are really carrying more diverse components. I mean, we're talking about, we always have had lighting and chrome decorative strips in bumper systems. We've been, things are being added like, radar systems, like aerodynamic panels, like sensors that enable open lift gates and things like that. So we're seeing more components that are very different from what bumper systems are inside of them, and it's increasing the functionality of it to be quite diverse. Aerodynamic panels have to be positioned in certain areas that funnel air to different points of the vehicle. The radar sensors are used for driver information, and also more and more are used for vehicle control. I don't see this lessening as we're going to more autonomous vehicles. I do see more sensors coming in that will help that functionality. But in all of that, we still have to maintain the low and high speed requirements that are there in the bumper system that in order to make it function as part of the vehicle. But really what we're looking at and want to focus on today is this metal impact bar that's behind all the stuff you see, or the plastic fascia. And it's this component that's right here that, really what we're focusing on this morning. So performance trends that are out there. We really are seeing, over the past years here, a decreased focus on low speed bumper performance. I mean, both the US and European regulations have really been unchanged for many years. The US regulation came in the early 70s. It changed in 1982. It hasn't changed in the last 38 years, pretty much been the same thing, exact same thing in that amount of time. The European bumper regulation came in 1959, and it has remained unchanged in the over 60 years that it's been on the books. So really, we haven't seen a lot of focus from a regulatory standpoint. Is the bumper regulations increasing in countries? Both Europe and Korea do have low speed performance of a bumper driven by insurance testing. This is sometimes referred to as the Danner test, more formally known as the R-car tests. These tests are performed on vehicles, and the insurance and are scored, and the insurance ratings or insurance premiums are set off the performance of those tests. At one time, it was thought that these regulations would go globally, maybe 10 or 15 years ago. That clearly hasn't happened. And so we have, again, it's been localized to those two specific countries where we've seen those performance, the low speed performance for our car. But lastly, in the US, we've really seen a decreased focus on low speed impacts caused really by two factors. The first being the market change from passenger cars to SUVs and light trucks. I mean, right now, the market clearly is selling more light trucks and SUVs than it is passenger cars. The significance is that the US bumper regulation applies to passenger cars only. So all the SUVs and light trucks do not have to meet any bumper regulation. Clearly unregulated bumper systems are being engineered for most of the vehicles in the US. But secondly, IIHS stopped testing for low speed bumper performance 10 years ago. They basically, their data indicated what our understanding is, their data indicated that there was really no correlation between the performance of this test and what they were seeing in insurance claims. Back 15 years ago, there was a lot of energy put into this, that manufacturers were taking this very seriously to make sure their vehicles didn't perform the worst, or some of them wanted to have their vehicles perform the best. Because IIHS stopped testing, that really there hasn't been the focus on that. And so what's happened here is that manufacturers really are not placing a high priority on low speed bumper performance in most regions. There is, though, an increased focus in high-speed crash performance, and we're seeing that because the vehicle requirements there are higher requirements for vehicle occupant protection. We're seeing this in the regulatory area of high-speed crash, and also in the consumer metric area, where there's the amount of forces and accelerations on the human. On the test dummies are continuing to try to make the injury levels lower to the occupants. So we're seeing those requirements come through. Secondly, there is an increased challenge for battery electric vehicles. Those challenges are based on really the requirement to protect the battery like a fuel tank. Many manufacturers are considering the battery to be like a fuel tank, and that the housings of it cannot be damaged for causes of, they don't want the unpredictable of what will happen if the battery is damaged. And so again, we have to protect the battery housing. And the battery is a larger component than a fuel tank. Usually because of the battery sizes, they come farther rearward in the vehicle, or they're wider in the vehicle. So we're seeing challenges in that particular area because it's a bigger area of the vehicle that can't be crushed. And lastly, battery electric vehicles are heavier than vehicles that are than other vehicles. And so the increased mass, again, is more energy in the vehicle that has to be managed in order to protect it. Also, it makes, because of all this happens in a lot of the batteries in the rear of the vehicle, it is tougher to meet FMVSS 301, which is a fuel tank test. And this is a rear test at a 70% overlap. And again, the goal is to protect the battery. And it's a very localized hit because it usually hits only one of the motor compartment, or the longitudinal rail structures, and the bumper is very much engaged in this to try to grab energy from all of the rear structure of the vehicle. So again, this makes this tougher to meet this test. We are seeing an increased number of impact locations at higher speeds for the vehicle also. I mean, the latest test that's happened is the IIHS small overlap frontal test. This is a 25% overlap. It came into about 5 or 6 years ago for the driver's side of the vehicle. Over the past 2 or 3 years, it's been added for the passenger side. This is a localized test, really outboard of the longitudinal rail, the front longitudinal rail of the vehicle. And it, again, has the bumper can play in this test depending on the crash strategy, and it can cause higher performance and higher requirements onto the bumper. Secondly, there's a new test coming out by Euro NCAP. They have announced that for 2022 model year, they will be testing a new test that they're calling the Mobile Progressive Deformable Barrier Test. This is a front test at 50% overlap. It is a car or vehicle to test cart test where both vehicles are moving. The test cart has a deformable barrier on the front of it, and the scoring of that, to do well on that, the scoring is a score of how uniformly the deformable portion of the barrier is deformed. And so where the bumper plays in with this is the bumper buckles, and it causes this deformation not to be uniform. So again, it's causing additional requirements to the bumper system to make sure that it can deform this barrier uniformly. So we are seeing increased high-speed crash performance, and it is driving new requirements into the bumper beam. Because these new requirements will affect the bumper beam material, because there will be a continued need for lightweight design. We don't see that going away just for the status of fuel economy requirements, and as well as battery energy users. To keep lightweight design is continue to be there, is continue to be in front of us. The performance requirements that are there for high-speed crash. I mean, the beam is the first structural component to manage energy in a crash. And so, and the beam kind of walks us a narrow window here, because the beam's got to be strong enough to actually deliver forces down through the longitudinal rails of the vehicle, which are the main crash components to absorb energy in the vehicle. But it can't be too strong, because it can't just be an infinitely strong beam, because it also has to absorb energy while it's doing that. So the beam is a balance component as the first component that touches to make sure that the energy is put into the areas that absorb most energy for the crash event. So the beam must work integrally with the vehicle structure in crash events. This has to be designed as a system, and there will be a system strategy developed of how to manage these load cases and how to manage these energies. Because high-speed crash requirements will drive stronger and tougher beams to fully engage the vehicle structure. They'll need to be stronger to make sure they can get the forces down to the rail. They'll need to be tougher to make sure they don't crack or don't tear off from the attaching parts of the motor rails. But we also have to remember that ultra-high strength steel is 4 to 6 times stronger than aluminum, and so it's important to keep steel under consideration when designing a lightweight bumper. Because if you look at, when you design a bumper, you put together a design, you optimize the material you're going to use, and you optimize the geometry of the beam itself. But at some point in time, you're going to have to, if you still have to increase strength at that particular case, oops, got to back up here a minute. If you still have to increase strength at that point in time, you're going to have to increase mass, so you're going to increase thickness. And because steel is stronger than aluminum, as you increase that strength, you will have to increase more mass of aluminum to get the same strength as you would for steel. That's why the different slopes are on these two lines, okay? Because steel will have a lower slope than aluminum, because steel is so much stronger than aluminum. So in the lower strength areas, aluminums will be lower mass and more cost efficient, and they will have a low dollars per kilogram mass savings, or how much it costs you per kilogram, because aluminum will have the advantage there. As we move along this curve and we increase our strength, the mass of the aluminum will increase faster than the steel, and it will depend on whether how much the aluminum, how much you're saving, and how much the vehicle team is willing to pay for mass savings from a cost standpoint. Because your aluminum is not only getting heavier, but it's also adding cost, because aluminum material costs more than steel. But there will come a point as you increase mass where the steel beam, because it is so much stronger, will be lighter than aluminum and lower cost than aluminum. And that's something where steel will again take an advantage relative to aluminum and still be a lighter weight design. So efficient steel designs can deliver increased strength needed for vehicle crash at a lower cost and mass. So we've done one effort that's happened over the past year or so here has been a benchmarking study we've done on beam material. This was a study of bumper beams on mid-sized cars, some in the industry called C-segment vehicles. It was a study done by, we gained data from A2Mac1, which is a company that does global benchmarking of automotive vehicles. And it was done for all regions of the world, model years 2015 through 2018. I mean, this is approximately 140 vehicles that were, for that particular time span that were used. And so we looked at bumper beam material, and for the front bumper beam, 71% of the beams are made out of steel, and 29% are made out of aluminum. For the rear bumper, we're seeing similar percentages for steel, 69% for steel. The remaining 31% is really divided between plastic and aluminum. This plastic, though the 12% plastic is largely one manufacturer, it's Kia and Hyundai, who have somewhat of a joint venture with a plastic bumper supplier, and so nearly all of their vehicles are plastic rear bumpers. But steel is the material of choice for bumpers. We're seeing that for both front and rear bumpers with approximately 70% of the market. And so front beams, notice the front beams were all metallic. And the reason for this is because of the tougher frontal crash requirements. Okay, it's predictable, steel's predictable, it's tough, and it's strong. We see that used for front beams, metallic for 70% for steel, and also even aluminum to make sure that the front crash structure is performing well. Rear beams will have to have higher strength requirements to meet the battery packs in electric vehicles. I mean, that's just a requirement. The rear beams will have to do that. And the use of steel will likely increase because it will have to meet the tougher high-speed requirements, and it will enable the stronger beams, again, where our goal is with lower cost and lower mass. But we did a case study here looking specifically at one front mid-size bumper beam, okay? And that we looked at a comparison of engineered cost and mass. And we took a production part, an extruded aluminum production part that's pictured here, we took it and compared it to a couple of designs that the team did. And the first being a hot form steel design. This was a beam that was designed and optimized with using computer finite element analysis. And then we took a third design of a roll form steel beam and optimized that using computer finite element analysis. Now, this is not a perfect comparison, but with the data that we've got available and the time frame we've got available and the resources we have available, it's worth looking at. And there was enough in looking at the data and looking at how it all the studies came out. It was enough to spend some time to really study Bennett to see if there's anything that can be learned from it. And so the requirements that were done because of the designs of the bumper, clearly all designs are designed to meet the R-car bumper test. This is, again, a 100% overlap test at 10 kilometers per hour. It is this barrier here that's kind of the salmon colored barrier that's 100 millimeters high. It was an assessment of how well the bumper performed to protect the vehicle in a low speed impact. The second requirement is the IIHS small overlap test. Again, this is a 25% overlap test at 64 kilometers per hour. This is the test that IIHS has developed to try to assess vehicle structure on the outboard corner of the vehicle. So just to look at each design individually. First, the extruded aluminum beam. We're looking at an assembly mass of 7.2 kilograms. I mean, this has an extruded bar in it in this area bent into a plan view. And also there were crush cans. The crush cans here are quite extensive for the IIHS SOF test. And also this center reinforcement was there for the R-car override test. So we see the design features in the vehicle, in this bumper design to meet the requirements. Also in the hot form steel design, this assembly mass came out at 9.5 kilograms. This is a two-piece beam design. You can see this section here, typically known as the B section here. It's 97 millimeters tall by 38 wide, very, very common for bumper beams. There's two pieces, and so there's a weld here at top and bottom that hold the pieces together. And you can see these two pieces here in the light color and the dark color, brownish color that get put together and assembled to become a one-piece unit as a beam. But again, we see the features for a center reinforcement and also the crush cans and brackets there for the IHS shallow offset test. That's the hot form design. Then we have the steel roll form design. That assembly mass is 9.4 kilograms, a little bit lighter, 1/10 of a kilogram lighter than what the hot form steel is, because there's no joint at the top and bottom. The beam is very similar, the same section, one piece roll form. Added to it again are the center reinforcements for the RCAR and also the crush cans for the IHS test. And just to look at some kind of cost comparison, the team had an independent outside supplier try to give us an estimate of what the engineered costs were for these particular assemblies. And so the aluminum at 7.2 kilograms had an engineered cost of $60.30. The steel hot form design at 9.5 kilograms had a engineered cost of $51.20. One way of looking at this, how much it is costing you to go to between steel and aluminum, at saving $9, you would also, if you went to aluminum, it would cost you $9, and it would be save 2.3 kilograms in mass. So the cost per kilogram that you're doing to go into aluminum, you're saving here in the case of steel is $3.96. From a steel roll form situation, again, the mass being at 9.4, the engineered cost of that system is $42.08. Cost per kilogram is $8.28. And these are fairly high numbers, and there's significant money here. I mean, this is $42, that's $18 of vehicle cost savings. I mean, that's significant money that maybe, steel offers the options to significantly reduce vehicle costs. And in this particular case with $18, there might be other areas of the vehicle that could save the same amount of mass at less cost. And that would enable vehicle teams to make decisions what's really best for their particular vehicle, because this cost per kilogram is higher than what's averaged. My experience has been somewhere between the $5 to $7 a kilogram range. So, I mean, we're up in the $8 range that might offer some different options for vehicle teams to, should they want to save the mass and also save the money in the bumper system. But let's look at the assembly breakdown of this. Let's take the roll form beam here for a minute, just to look at the assembly breakdown a minute of exactly what we're looking at. First is the bumper beam. That's the typical, the blue component right here again. But the second area is this crush can, the crush cans area out here. This really is dependent on the vehicle crash strategy. I mean, one is it requires as if the vehicle has to meet the requirement for the IHS test. You wouldn't need this outboard crush can if you might not need it if you didn't have to meet that requirement. In addition, the vehicle crash strategy for the front end, might not require this type of engineered crush can either. I mean, I've seen vehicles that have done quite well in the IHS test that had nothing out there, but they had other features in the rail or other features in certain areas that enabled it to do well on those tests. So again, that depends on what strategy is there and what's the best for the whole vehicle system of how that's engineered and what is the most mass efficient for the whole vehicle in that particular case. So that is in question whether we would have vehicles that might not need or might not have to have these particular crush cans on the outboard side here. In addition, the center reinforcement is only needed for the RCAR bumper test. And so this particular thing is if this bumper didn't need to meet that requirement, which if it was only required for or was only needed for Europe or Korea, there's large regions that don't require it. So again, that is kind of an optional component also. So the point here is let's focus for a minute on the bumper beam itself, okay, of what is the bumper beam here itself. So let's look at these three assemblies and do a little bit of analysis over where the mass is coming from in the assembly of each one of these three. So the first being the aluminum. Again, total assembly mass is 7.2 kilograms. The beam is 4 kilograms of that, or 55% of the total mass. The remaining 45% is in the crush can and in the center reinforcements. In the steel hot form design, it's 9.5 kilograms, and the beam itself is 4.3 kilograms, I'd say, of that, or 45% of it, and the remaining 55% is in the crush cans and in the reinforcements. For the steel hot roll form design, that's again, total mass is 9.4 kilograms, the beam being 44% or 4.2 kilograms, and the remaining 46 or 56% being in the reinforcement and crush can. And so the point here is that the aluminum beam, if you look at these percentages, the aluminum beam has a higher percentage of the vehicle mass, system mass. And again, this is because it appears that with that particular crash strategy, the beam has to be stronger, and if it's an aluminum beam, it has to have higher mass to enable to meet the requirement. And aluminum beams, the steel beams are also less than half the assembly mass, okay? So we're seeing this down at 44 and 45% versus the 55% for aluminum. And so again, the steel is stronger and it can be more efficient at handling these particular loads. So if we look at these, again, beam masses, we're not looking like a big difference here. There's only, 2 or 3 tenths of kilogram of difference between the steel and aluminum here. And so our goal needs to be to continue to look at mass reductions for the steel beams. Just to throw a proposal out there, okay, of what something might be. Here's a case study. Again, here's our B-section beam that we've been looking at for the past few minutes here. It is 97 millimeters high, 38 millimeters wide. But if we looked at a proposal that said, let's remove this center area here that has the 2 horizontal webs in it, and let's put a single horizontal web and tie the back together. I mean, this is a section that bumper manufacturers have the technology to make. Okay, it's out there. Okay, if we did that just by reducing that amount of steel, we would see a 10% reduction in vehicle mass. Okay, and so if we go back to our chart to look at where that ends up being beam mass, here's being the original mass. If we're reducing that by 10%, then our new beam masses are 3.8 and 3.9 kilograms. We actually are seeing less mass in the steel beams of 0.4 of a kilogram than we saw in the aluminum. Okay, so again, higher strength beams, steel can enable, has the technology to save mass over aluminum on beams. In conclusions, or just some conclusions, general conclusions to pull together here. Increasing high-speed crash requirements do create a higher need for higher strength beams. Okay, that's out there. The high-speed crash requirements are coming and they're there. That will happen. The higher mass battery electric vehicles are creating additional performance requirements for bumper beams in high-speed crash. We're seeing this as happening as part of the vehicle structure. And really, ultra high strength steel enables a stronger bumper beams at lower mass and lower costs. And our goal of today was to show you kind of just to challenge your thinking to say steel can be a win-win. It can both save mass and save costs based on where we see the trends in the marketplace going. Okay. And with that, we'd like to introduce to you the Steel Bumper System Manual version 7. This is an in-depth bumper report on steel bumper systems, including information on the material properties, manufacturing, and product design. This has really been a culmination that we've been working on very, very much for the past 8 or 9 months here. This manual has been out, although this is a significant revision from version 6. It took a reduction of about 30%. I mean, the version 6 was about 150 pages. This is down to about 100. The goal is to be much more focused and be more better information in a more compact, focused document to help the industry. It was done by 3 of us, really worked on it together. Hisham Hassat wrote the chapters on material and also on welding and manufacturing. Project manager Michael White led us both. And I worked on the bumper portions, and we worked really great as a team. And it was, I think we've got a significant rewrite this we really think will help the industry here with this version 7 of the manual. And with that, I can entertain any questions.
Thank you very much, Stu, for your comprehensive presentation on behalf of the American Iron and Steel Institute's bumper team. Our webinar audience does have a few questions for you. I'll read those questions and then as they are submitted, and then allow you to address them as we have time remaining. So I'll start with the first question. The first question, Stu, is what kind of changes will the new MPDB bring to bumper designs?
Yeah, that's a good question. We know some of them because we've developed some solutions. I'm not sure it is a development project, and I think that some manufacturers might take different strategies than others. Clearly, the changes I think just generally will be is the bumper, in order to deform that deformable very evenly, are going to have to be taller, possibly. And also the area right in front of the rail, how far the beam extends out beyond the rail and the height of it there are going to be very critical to again, deform this barrier evenly. And again, keeping the beam from buckling, I think, appear to be some of the key ingredients that are going to need to be in the bumper features that are going to make it do well in this test.
All right, great, Stu. Second question from our web participants is the hot stamping used using 1500 megapascal strength ultra high strength steel?
Yeah, yes, it was. Yes, it was. Mm-hmm.
All right. Next question. Let's see here. Is there any hybrid designs where we can get the benefit of using different materials out there?
I mean, obviously there are a number of ideas how to make designs more efficient from a cost and mass standpoint. I think that hybrid designs of maybe different materials could offer some advantage there. We didn't study it or understand that. I mean, that was, but we kind of, again, we're focusing on steel. But I mean, obviously that would need to be studied, or what the advantages of each particular hybrid design might be. So.
All right. Another question from some of our webinar guests is, what do you think would be the performance impact going to the 10% lighter steel bumper design?
You know, that's a good question also, and because obviously my little proposal was without any, we didn't take it back and rerun the analysis with it. You're changing from the B section that really has open lobes on the back to a section that is a window pane section that is fully closed out on the back. So where you lose a little bit of strength in not having an additional horizontal web there in the section, you gain strength by having the backside totally closed off. So, I mean, there's a plus and minuses there. I don't doubt that there might have to be a little tuning in that particular case once we had once you actually saw finite element analysis that would see where the performance is at. But our experience has shown that it doesn't appear to be you have to add a lot of additional mass because we took a horizontal web out. Because you gain strength when you close off the back wall, it's kind of a balancing act that you remove that one horizontal wall and you add strength with closing out the back wall, and that enables the section to perform quite equivalently relative to a B section.
All right, thank you very much for that answer, Stu. Another question for you. Do OEMs design bumpers for global vehicles or for local vehicles?
Yeah, that's a really good question too. The answer is yes, they do for both, I believe. I mean, I think that it depends on the vehicle, I believe. I mean, if and the vehicle volumes that are going to go into each region. I mean, if you had a vehicle that you would have the largest portion of your volume in a certain region, you might make the decision to only have one bumper system, and you might export to other regions, and that bumper might have more requirements in it than the region it was going to require. Okay, for instance, if you had a vehicle engineered for the U.S. bumper regulation is the toughest bumper regulation in the globe right now. You could send it to other regions, and it would be legal for bumper system regulatory anywhere. But again, you would be over-engineered if at the point at which you have larger volumes of a vehicle. Say, for instance, you were sending a vehicle to China, that same vehicle to China. If the vehicles were high in China, you might say, well, I can redo the bumper bumper system, do optimization of that bumper system to save some cost, save some mass. So then you would do 2 bumper systems because it would make sense from a cost standpoint. So it'd be a business case scenario really is the answer to the question over whether you would design one global system for the world or whether you would design separate systems in order to optimize cost and mass between particular regions.
Great, thank you very much, Stu. This question is kind of a multi-question. I'll read the whole thing, and if you need me to go back and read it again for you as you answer, that'll be totally fine. So it says basically, on your experience with geometry, have you looked at shortening the beams cross car? It says also, do you normally use interface plates with the front structure or slot the beam directly into the front structure?
Okay, so the first part of the question was relative to extending the beams, okay? The beams getting longer are really driven by what the requirements, in the case of low speed, where the corner hits on the low speed is. Because of how the vehicles are being in the plan view, kind of a rounded shape, that's driven the corner impacts inboard. So the beams have actually gone shorter, I believe, over the past years as those corner hits have moved inboard. Relative to what's driving the beams back out again, clearly the IIHS test is making longer beams to try to engage the barrier at a 20% or 25% overlap. So I mean, that's clearly, what's pushing it back out. I also believe that the new Euro NCAP test, MPDB test, will move that beam back out again. Okay, and so in order to do well on that test again, it's going to require that beam be spread out. So I really believe that that's pushing the beam back out again. You wouldn't, again, the length of the beam would be determined by what requirements the vehicle has to meet. You wouldn't want to have the beam any longer you need to because it is cost and mass. So relative to the second part of the question, which is mounting, question of is it better to have mounting plates or is there some kind of maybe telescoping design is kind of what I'm taking by the question. No matter where you go with the mounting structure of it, I mean, if you go to a telescoping and design a certain amount of the the beam or the portion of the beam assembly has to telescope into the rail, so there's a certain amount of mass overlap there. Wherever you go with that, there's a certain amount of inefficiency in that joint. We've done both of those joints, in the past. I've had experience with both of those joints in the past. Each one has positives and negatives. Really, I mean, it depends on, the particular situation, the vehicle configuration and packaging in some cases, and also some performance requirements, which one you would go to. Clearly, we see a lot of flange mounted beams out there. And we have seen some telescoping designs, that go into right now. And I guess just looking at the industry, the flange mount seems to be favored by more manufacturers than the telescoping design.
Okay, thank you. Thank you very much, Stu. Next question. As third-gen steels become more developed materials and joining becomes more understood, how do you think that this will affect bumper designs?
Okay, so third-gen steels. I'm not totally an expert in steels, but I mean, third-gen steels, I believe, are going to continue to be stronger and tougher, is what I understand it to be. Again, that's going to help steel in a particular case as the material of choice, because those beams will continue to add another level of development of technology that can be made into configurations of bumpers, and they will perform at a higher level. And as I say, I really see in that the high-speed requirements continuing to increase that will play well, and third-gen steel should help that. Again, bumpers continue to be cheaper and lighter for future models. So.
Okay, great. Thank you so much. Next question. Based on the benchmarking study, there is 29% aluminum in front bumper beams. Is this mostly for premium vehicles applying aluminum, or is it related to electric vehicles?
In the study was not, I don't believe there were any electric vehicles in there. There were a couple of hybrids in there. I didn't do a correlation between the hybrid and the whether they for sure had aluminum bumpers on. I will say that the premium vehicles is where you do see aluminum more than you would see it on the more economical cars or whatever. But I mean, this was though a study of mid-sized cars though, which is is not the premium segment. It's more of the is your family of vehicles like the Hyundai Sonata, the Honda Accord, Toyota Camry. That you're looking at that level of vehicles, and so just generally. This is more of a family vehicle segment than it is a premium vehicle segment. I guess I'll say it at that were reviewed. So I don't know that I saw any particular correlation between what vehicles were using aluminum versus steel.
Thank you very much for that answer, Stu. We got a couple more questions here. Next question is, do you think OEMs will soon come up with different bumper standards to meet high-speed impact like SORB and battery vehicle architecture?
Yeah, I mean, I do think that there's going to be innovation at every manufacturer to try to figure out how to meet all these requirements, because there's a lot of new requirements coming in that are quite are difficult requirements. They're not easy to get, and I think it's going to cause innovation, which is going to cause different vehicle manufacturers to have different strategies. And I mean, I think you're going to see a lot of some variation between each company and what they do to how to meet all these requirements. So.
All right, thank you, Stu. Next question from our guest is, for steel beam applications, what would be the percentage of using in zinc coated steels? And for hot stamp beams, what would be the coating, uncoated or aluminum silicon coated?
I believe that my experience is I have not had a lot of experience with hot form beams. However, I do think that all the beams that we used were silicon coated just for the rust protection aspect of it, not only getting from the vehicle for the bumper manufacturer to our assembly plant, but it also again did provide that extra level of corrosion protection once it went through the paint shop at the assembly plant. That again, you had kind of a two-barrier corrosion protection there. So I believe, what I have seen in a limited snapshot of hot form beams has been that the silicon coating is what most manufacturers probably will go to eventually, if not are there right now. So.
All right, thank you, Stu. Next question is, could you give us a little more detail on what factors can be considered when calculating engineered cost? Is it the difference in manufacturing cost?
Okay, so engineered cost. Oh, well, does somebody else want to answer? No. I'm sorry. Yeah, the engineered cost was looked at. It is the manufacturing cost. It was looked at, how much material was there, the cost of material, and looked at each of the individual processes. For instance, in the case of a roll form steel, you had the material itself, you had the roll forming process, there was a bending process there, you had stamped components that were added to it, the welding operations to put on then. Again, all of these steps are put together, and that's what made up the engineered cost for the particular parts.
All right, thanks very much, Stu. Next question is, for the roll form beam, what was the ultimate tensile strength of the material?
I think Michael, help me on this one. It was 1,500 at least. Might have been 17 or 1,900. I think we used 1,500 when we did that study. Correct?
Yeah, that's what I believe it was. It was 1,500.
Yep. Yep. So.
Okay, next question is, in general, who is design responsible for these systems? The OEM or tier ones? Or do you work with the OEMs or the tier ones? Do they work together to get these systems all set up?
That's a good question. I mean, each automotive manufacturer might have a little different strategy in this particular situation. So you've got there's two factors going on. One is you have to look at the strategy that the particular manufacturer has. Some manufacturers like to have their own designs that they own, okay, so that they can source them wherever they want to do, and they put their technical capability into it. You have some, vehicle manufacturers that want to be more maybe collaborative with their supply base and want to maybe have the design be from a supplier and bring it in. So I mean, you have the opposites to what's going here. So you have the one factor of what are the particular automotive manufacturer's strategy with their supply base and their crash management. Okay, so that's number one. On the other side, what you've got is you've got you've got what is the bumper supplier's manufacturing capability. Okay, each particular bumper supplier, has a little different capability, and on that, none of the processes that are out there, largely line up between all of the suppliers. So it becomes difficult for a auto manufacturer to say, I'm going to design a bumper and I'm going to source it, and I'm going to source it with 6 different, send a quote to 6 different suppliers, and they're going to, quote this design and give me back a comparison, because every bumper supplier's process is just a little bit different, and those suppliers have obviously optimized those processes based on their technical innovation to try to make their particular process better. So I think, where you end up with this is that you have a little bit of both going on. I mean, you can take the avenue as an automotive manufacturer to say, I'm going to go with one supplier and use their technology and bring that in and use, it'll be their design. That is a strategy that a particular manufacturer could have. Or you can kind of look at collaborative to say, we're going to start out with a design and then try to work with suppliers to see, which one eventually, once we source the thing, to work with their particular design to bring the design features in that their manufacturing capability is enabled it. And so, ultimately, your goal is to have the lightest and cheapest beam. And how you accomplish that really is, again, how technically capable your company is in bumper systems and meeting the requirements, what your company feels, what the strategy of your company is relative to how they work with suppliers, and how that all comes together. So it's a little bit of a complicated question, but it's one that depends on what each manufacturer's strategy is, as well as the capability of the bumper suppliers that they use. So.
All right, thank you very much, Stu. Next question from our guest is, in addition to bending strength, does torsional strength come into play during impact? How could this affect the design?
Okay, that's a good question. The area where we saw a lot of effect on torsional strength was in the area of when you had the R-car bumper test. That loads the front beam, maybe the top half of the front beam, because the barrier is higher than the bumper in many cases. And so torsional strength was important with that particular load case. In the other load cases, we don't see as a high a priority of that. The low speed cases, the pendulum impacts for the regulatory requirements, the pendulum just doesn't have the energy that our car barrier had. So I mean that we didn't see as much effect on torsional strength in those particular load cases. And from a high speed standpoint, a large of it is barrier where it loads the beam evenly top to bottom. So we don't see torsion as much of an issue. So the only point at which torsion affects, I would say, is if a vehicle has to meet the R-car bumper test, that then becomes a factor in how well the section can handle torsional loads.
All right, thank you very much, Stu. Next question from our guest is, what kind of changes do you see for front bumpers on vehicles that don't have engine blocks, BEVs?
Okay. Again, in this particular case, it's once that is a a large component, obviously, in the front of the motor compartment that affects how much the vehicle structure can crush. And so, when you remove this large component, it offers additional crush zones. I don't know that I see radical changes to the bumper because I think the bumper is one component of a total crash system. And so once the configuration of the motor compartment is, I think the bumper will work with the other structural components in the front motor compartment to deliver the crash strategy or the crash requirements that are needed by that particular vehicle. I don't think that because there's not the motor is out in something smaller is in its place. I think that if it enables shorter fronts, I think that will get, the effort will be to try to optimize that system over again. I'm not sure that it would be a significantly different design for the bumper, though. I guess I'll say that.
Okay, thank you. Thank you very much, Stu. We have another question here. The graph where the aluminum and the steel crosses, at that point,
Yeah.
is there a weight that is correlated to this?
Let me get back to there. They're trying to get there quickly. Hang on. That is a very good question. The experience that I had on one bumper was, you're talking about this graph right here. Hang on, this one. Where is this point and what mass is this point here? I don't know that there's one answer for every particular vehicle. My experience has been with a beam that once this got to be, in the area of 6 to 7 kilograms, we crossed that line. And this is a heavier vehicle, though. Okay, so I think it will depend on the size of vehicle that you have. This was an SUV we were engineering that line was somewhere between 6 and 7 kilograms. You look at the mid-size car example that we had, it looks like that cross line is somewhere down around 4 kilograms, between 4 and 4.5 kilograms, somewhere in that area. So I think it will depend on the vehicle mass and also the crash management strategy of how short is your front end, how much strength does the system that you're trying to manage the crash under require. It'll move, I think, based on some different factors of the vehicle dynamics.
Thank you very much, Stu, for that answer. We have time for a couple more questions. Next question would be, would you expand a little on crash philosophy, which don't use crash cans?
Okay. It really depends. Again, the crash management strategy is what a particular the decisions that are made by the safety community of a particular vehicle over how they're going to manage it, run safety, and also the structural components of the front of the vehicle. So for instance, vehicles that have not had any changes to the bumper at all, usually there is some kind of significant bracket right ahead of the wheel. Okay, that's been seen in various benchmarking that's been done. There's been vehicles that managed all of the energy right by adding reinforcements behind the wheel to the front body hinge pillar area of the vehicle. And so there, again, you can see there have been different solutions that are out there. I think that these solutions have evolved a bit over time. When IHS brought this in, obviously, manufacturers, re-engineered what they had that was in production to try to help meet it. And that might have resulted in some solutions that were not necessarily optimal. So I think now as the requirement has continued to be on for a number of years, we are seeing, what are different strategies that are coming into the vehicle marketplace that are maybe determined to be more efficient. So I think that's why you could see maybe a vehicle that in the past, they added additional reinforcements right rearward of the tire at the front body hinge bevel to do well in this particular test, they might have determined that that was a lot of mass added to the vehicle and a lot of cost. They were able to maybe change their strategy to add, to engage the crash energy earlier in the event by putting some reinforcements maybe farther forward on the bumper rail, or you're seeing changes to the bumper beam itself to try to engage this and absorb energy earlier in the crash event to be more efficient, more cost efficient, and more mass efficient. So, I mean, I think there's still a number of solutions that are out there being viewed. I think generally, where it is, I think less companies are trying to reinforce the bodies themselves. They're more trying to absorb energy farther forward in the vehicle just by just some of the evolution of this design requirement. So.
Thank you so much, Stu. At this point, sorry to say we're running out of our allotted time, and we won't have the opportunity for Stuart to answer the rest of the questions in this webinar session. But I will get the remaining questions answered offline by Stuart and get the information to you. I am the program manager for the AISI bumper team. My name is Michael White. My email address is here on screen. It's mwhite@steel.org, and I can be reached at the number on screen 248-945-4779. At this time, I would like to turn it back over to John Catterall, Vice President of Automotive Program for American Iron and Steel Institute. John?
Thank you, Mike. And I'd like to thank Stu for a great presentation, a very detailed Q&A session. It's clear that Stu is an expert in this area, so we appreciate his presentation today. I'd also like to thank the whole team that made the webinar possible today, and also the bumper team that updated the manual, which you can, just to remind you, you can download both the manual and a copy of the webinar today from autosteel.org website. So please go ahead and do that. And then the last slide, if you want to go to that, Stu, for me. So just a reminder, we actually have another webinar in the little series we're doing here. We're not doing one next week because it's obviously the July the 4th week. But July 8th, we have another webinar around mixed material joining. We have Brian Masick from FCA will be taking us through the results of that. This is also a body of work that we would have presented at Great Designs in Steel, and obviously did not have that opportunity. So please, the registration will open up on Monday for this. You'll be able to go to autosteel.org and register through the website also. So I appreciate everybody attending today, and have a good balance of the week. Goodbye, everybody.